All right, so our task. Our task is to create a couple of new equations that basically are like super equations that takes the three equations, what they're capable of dealing with, and gives us a more broad toolkit to use. We'll still use the three equations very regularly, but the other couple equations are more beneficial for various situations. Now, one equation doesn't even require us to combine anything. We could just take this guy. We can just take this guy and we can untangle him. And here's what I mean. So instead of writing it like A is equal to delta V over T, I can write it as A is equal to your final velocity minus your initial velocity divided by T, right? Because that's literally what delta V means. It's take the final velocity minus the initial velocity and divide it by the time, right? Then we can rearrange it a little bit. I would multiply both sides by T, this side by T, this side by T. I get my acceleration times my time is equal to the final velocity minus the initial velocity. Now, usually the way it's expressed and how it would be expressed on a reference table on the Regents or in AP, we would add V naught to both sides. And so we would get the final velocity for any given situation is equal to the initial velocity plus the acceleration times the time. We consider this like a fourth equation. It's not a new equation because basically what I wrote as 2 and what is 4, they're exactly the same equation. The only difference is for 4, I've just untangled it a little bit so that it's, more accessible. It's quicker, like I'm trying to just figure out how fast something is after a second or two of accelerating. That equation's a quicker way to do it than having to plug into the A and then rearrange it. So it's a useful tool. Now, there is one assumption I'm making throughout this. And what is the assumption I'm making? Anybody know what the assumption I'm making here for this to be true? What's the assumption to assume that your final velocity is going to be equal to your initial velocity plus acceleration times time? Anybody? Catherine?
Acceleration constant?
Yeah, it's critical, right? This value here must be a constant change throughout the entire situation, right? This guy must be constant. Must be constant. If A was getting larger, A was getting smaller during that time interval, well, you'd wind up at a different final velocity than what you would expect. And in fact, all of the equations of motion rely on that underpinning. These equations of motion only work if your acceleration is not changing. You're not getting faster, not getting slower during that time frame, right? Yeah, very important. And in fact, if you have a situation where acceleration is non-constant, you just throw all these equations right out the window, and then you go right to everybody's favorite topic, calculus. See, calculus, integrations and derivatives. That's where you'll have to go. But thankfully, for this class, we're not worrying about those kind of fun adventures. Wait until C, APC, and then you can have all the fun you want with calculus. Yeah, so that's easy enough, right? All right, the next couple equations are a little trickier, and they're going to require a little bit of algebra. So here's what we're going to do. Essentially, what I'm going to do is I'm just going to combine all three equations together. I'm just going to make one Frankenstein equation. Allow me to show you how it works. Step 1. I identify that this equation and this equation, they're both equal to the same quantity, right? You see that? Average velocity is delta x over t. Average velocity is also equal to initial plus the final divided by 2. So all I'm going to do is I'm just going to set them equal to each other. So I write, I'll just write it over here again. So average velocity is equal to delta x over t. Average velocity is equal to v plus v naught over 2. And we combine. So I set, now I can set them equal to delta x over t is equal to v plus v naught over 2. Since they're both equal to the same thing, you can set them equal to each other. Yeah. Now we got that. Now we got too many variables going on here. You could deal with final velocity and initial velocity, but most of the time in a problem, they're not going to give you final velocity or they're not going to give you initial velocity. They only give you one of those two things. They don't usually get, not easily going to figure out both at the beginning, because that's probably the hardest thing to measure, is the starting velocity or the final velocity. And the essential issue here is that to measure these velocities are what we call instantaneous, meaning it's the velocity. These are velocities at a specific moment, right? The v naught is the at the moment I start. The v is at the moment at the end of the time interval, which are hard, very difficult to measure in practice. So what we're going to do is we're going to just get rid of one of those two, so we don't have to worry about one of them. And typically what we do is we eliminate the final velocity, because usually it's easier to remember the initial velocity, because most of the time, and oftentimes when we do problems to simplify it, we start from rest. What is the word from rest? You should know what the word from rest means, right? From rest, you definitely should. I'm not even going to ask this one. This one you should all be familiar. Rest. From rest, is we use it all the time, just means v naught equals 0, right? That's important. So what I'm going to do is I'm going to eliminate the v naught. The way I'm going to do it, or actually I'm going to eliminate the v. That's what I'm going to do. I'm going to eliminate the v. And the way I'm going to do it is I'm going to use the equation we just built, right? The one that I said was just untangled right here. So since I know my final velocity is equal to the initial velocity plus the acceleration times the time, I'm just going to take this guy right here. I'll put it in green. This velocity, and I'm going to substitute in for where that is in that equation. So now the new equation becomes your change in position divided by the time is going to be equal to, and I'm just going to substitute these values in. It's going to be v naught plus at plus v naught, right? That's what I just, substituted. And I take all that bit and divide it by 2. So far, so good. Any questions or confusion? Anything we're having some trouble with on that? For those of you that are comfortable with algebra, this should not be a grand stretch, but it's something you really want to understand the inter way it's done, because on the AP exam, you're very rarely going to see numbers. They don't give you numbers. Who needs numbers for physics? Because physics is not about the numbers. It's about the relationships between the quantities. And so the numbers are not what is important. It's how do we manipulate variables to get to where we want to be. So a derivation, and this is what I'm showing you right now, is what's called the derivation, is critical, especially if they give you some wacky situation. They will ask you, give us the equation that describes where this thing's going to be based on these variables. So what I'm doing, they're going to expect you guys to do on the AP exam, just so you know. Not this particular one, right? They'll come up with some crazy situation, but it's the same kind of idea. So at this point, we could distribute things along the way. So we would get, I'm going to multiply both sides by t, right? Cancels out the t there. So I get my change in position, delta x, is going to be equal. So v naught plus v naught would be 2v naught divided by 2 plus, oh, and there's a t, factor the t times the t across, 2v naught plus it's going to be at, that's at times t, so that's t squared divided by 2, right? I just distributed. That's what I did there, right? Distributed the t, because it's the t times all of this business, right? And then usually we simplify it as your change in position is going to be equal to the 2 cancels out with the half. You get v naught t plus 1/2 a t squared. This is like the bread and butter equation of physics. We use this equation for all sorts of wonderful uses, and the reason is very simple. It includes change in position, displacement, which is really nice, and it includes if you're accelerating or not, which is really nice. If I'm not accelerating, it basically reduces back to just what the basic equation would be, the velocity times the time, and you can rearrange it. Or if if I have no initial velocity, it reduces just to this, which is also a very useful tool that we'll use oftentimes. So very, very useful. There's also an alternate one. I'm not going to derive it, but you could derive the same equation for final velocity. That happens. It's happened in the past where you might have to derive for final, but it's not typical on the AP exam, and I'm not going to derive it. That's more like an exercise. If you're curious, you could make a similar equation dealing with just final velocities if you wanted to. Now, typically, well, this is nice. It tells us our change in position. The way we finalize it, so we can just locate where we are at a moment in time. See, this deals with just the change in position. If I want to know where I end, like the exact position where I end, we untangle this. We write it as x minus x naught is equal to v naught t plus 1/2 a t squared. And the most general form of this equation typically is your final position x is going to be equal to your initial position plus your initial velocity times the time plus 1/2 the acceleration times the time squared. This equation is the equation that will locate where you're going to end up at the end of a time interval if you know where you're starting, like where's your initial position in whatever coordinate system you're using, if you know the initial velocity, and if you know the acceleration during that time interval. Yeah? Questions, concerns, wonderings, anything about this that you want me to explain a little better or anything like that? Yeah. And if you're confused, I'll post a video on this and you can always just rewatch the video and get a little more, right? Now, this is nice. This equation's cool, useful a lot. But there's some situations where they'll tell you maybe your change in velocity, but they won't tell you how long it took. They won't tell you the time. So we call this the time dependent. This is the uh, time dependent equation of motion, right? Typically, if you're giving a time frame, that's where this becomes really useful because you'll notice there's a time term in most of the things in the problem, right? And in fact, this becomes a quadratic. Sometimes you'll have to solve the quadratic to locate where you are. This becomes a much, see projectile motion in the future. We'll chat how the quadratic equation will come back to haunt us. But sometimes you want an equation that doesn't have time, right? Maybe I don't want to deal with the time at all. Like they don't give me the time in the problem, right? So in that situation, we're going to do exactly the same thing again, right? So we're going to write, I'm going to start. I like to always start from the same root. There's a lot of different ways to do this derivation. I like this particular way because I always start from the same thing. I'm going to write this as the same. I'm going to write the same start, right? So the same start being that your delta x over your time is equal to the final velocity plus the initial velocity over 2, right? I'm going to start the same way, same exact root. Only this time, instead of eliminating one of the initial or final velocities, I'm going to get rid of the time. Because the time, again, works in the time-dependent equation, but I want a time-independent equation. I want one that doesn't involve time at all. So it's actually going to be a very similar start. I can use the same. What I usually do to do this, I multiply both sides by t. So I take this side times t, because I like working with it, time being in the numerator. I don't like dealing within the fraction. It's always annoying to fractions, right? So I can write my change in position delta x is equal to v plus v naught over 2 times t, right? And if I want to make it even a little more simpler, I might write this as 2 times delta x is equal to v plus v naught times t, right? Nice flat equation, don't have to deal with fractions at the moment, right? Then all I'm going to do is I'm going to replace t. Now, where do we replace t? Well, I want this to deal with acceleration because I want to deal with a situation in case the thing gets faster or slower or changes its direction, that kind of bit. So the way we can replace that is I can just go with, I know acceleration is my change in velocity divided by time. So if I want to get rid of the t, I'd multiply this side by t. I'd multiply that side by t. And I would divide this side by a. And I would divide that side by a. So I can set that the time is going to be equal to your change in velocity divided by the acceleration. Yeah? So far, so good. Now that I've got that, I can just take the old time and plop it in for that time right there. And we get 2 times my change in position is going to be equal to the final velocity plus the initial velocity times delta v over a. Now I'm going to write that as final velocity minus initial velocity over a, because that's what delta v means. So that's v minus v naught over a. Yeah? Times a on both sides. So I get 2 times a times delta x is equal to v plus v naught times v minus v naught. Now, those of you that are fine math students might recognize these two terms. What is this equivalent to if we distribute them to each other?
Difference of squares.
That's right. So this becomes, it's v squared minus v naught squared is going to be equal to 2a delta x, right? And if you don't know your difference of two squares, feel free to take v times v and then v naught times, you could do the FOIL if you really, really are desperate. But a difference of two squares is an easy way to solve this last guy. And the closer down, all we got to do now is, usually they like to put it in terms of the final velocity. So the way it's written on the reference sheet that they give for the AP exam, they write it as v, your final velocity squared, is equal to your initial velocity squared plus 2 times the acceleration times the change in position delta x. Yeah? Any questions, comments, or wondering? So let's write down all of our equations. Now we have all the equations of motion, and all you got to do is write them down. Typically, I write them as average velocity is equal to the change in x over t. I write also that the average velocity is equal to the final velocity plus the initial velocity divided by 2. We write acceleration is equal to change in velocity divided by time. We write the final velocity is equal to initial velocity plus the acceleration times the time. We write x is equal to x naught plus v naught t plus 1/2 a t squared. And our last but not least, v squared is equal to v naught squared plus 2a delta x. 1, 2, 3, 4, 5. Typically, they go with 5. They say these are the 5. But there's like the hidden brother that's hiding back there. This guy, that's like 6. They don't put this on reference tables, but this is like a linchpin that we use. As you saw, I used it for both the derivations. Someone write something in the chat. What is that for? Which one? I didn't catch when you asked that one for, Nina. For the last one I showed? Nina? Yeah, the last one, we use this equation in situations where they give us these variables, but you don't know the time frame. So for example, let's say I drop a ball and I don't know how long it falls. Like maybe I can't time it very well, but I do know the height it's falling, like the change in position. If I know the acceleration, which we do, it's like 9.8, which we'll talk more about later. You can use this equation to figure out how fast something's going to hit the surface when it hits. It's really useful in situations where time is not easily measurable. Yeah. All right, that's it. That's the equations of motion. Get to know them, get to love them. You'll use them a lot, especially when I start giving kinematic problems. But there you go. Any other questions? All right. Well, I'm going to stop the recording. And I'll post that later on when you have some more questions.